next week, we're going to have the exam review on December 4. So we do not have class on the course on December 27 because of the, of course, we deserve break for that. And then, yes, so I hope that all of you are doing fantastic today. And then we're going to have the exams on December 4, right? So we have like 2 weeks to prepare for the exam review. I post solutions on it and let me know if you have any concern. There are actually some questions that will not be put on the exam, like chapter 5 and 13, so you don't have to worry about those. Okay. And then for those of you who have like some trouble regarding the homework and classwork, just let me know what it is. I will grade all of them and post solution so I can have the topics and the certain, material to study before the exams. So if you have more concern, just let me know during the office hour. I've been waiting for like an hours and nobody joined the office hours. What happening, people? Yeah, I'm waiting for so long and still nobody came. You gotta be kidding me. So and today we're going to be working on chapter 12, and I hope that this is going to be the chart, the final chart that we have to use on the table. So making sure that we grab it with you. And other than that, it's pretty good to go. And let me just tell you that the final exam will be on December 18th. So it should be a month from today, less than a month from today. So time flies really fast. I still remember the first day that we joined to this class, and we talked with Chu Circle, and people just saying, well, the whole statistic is about the sum of Chu Circle, like this population and sample and all kind of thing like that. It's been a great pleasure. So so we do not have class next Saturday. Just want to make sure that you're not going to join on Zoom on November 27th. So we're going to have class for the second exam review on December 4, and then we go to take the exam after 4 p.m. So the exam should last within 24-hour time frame. Just want to let you know that we basically have the same format and the same kind of like the time length compared to the third exam questions. Okay. Yeah. I apologize, so I couldn't really make it like from my syllabus because we have to hold up for a week for certain lectures. And other than that, everything should be perfectly cool. If you have more concern, just let me know. Okay. So we're going to work with chapter 12. So I heard some of you have some trouble with the chapter 11, right? So we're gonna do the standard deviations. I'm sorry, we're gonna compare the standard deviation between two means, and then we definitely gonna have some questions and some calculation regarding the computing the degree of freedom, and also there are actually some questions when you want to compare the two mean population. Okay. Now we didn't have class, Jennifer. Thanks God. I have to on Zoom on Saturday. Yeah, definitely not gonna have class for sure. Even if you want to join Zoom, I won't be here for 100%. So don't expect me to be here. So we work really hard for that. We deserve some, Thanksgiving break with family and friends, and have some party at night. Play some, games along the way. That's gonna be a lot of fun, and apparently that we're going to have the next reviewed on December 4 and the exam on that day. So you gotta be really, really careful with that day. So I do not really expect you to take the exam at 1 because I feel like I have to go over all the review questions before 3:15 p.m. Okay, so I have to spend at least 2 hours for it, and then after that you can take the exam. We can take the exam from there. Okay, and then later on when we come back on December 11, I will try my best. This time I will try my best to grade the exam. So just want to please do me a favor. I'm going to put some fill in the blanks, and then of course you have to show work how to get those answers. Okay, so if you simply fill in the blank, you're not going to get the full credit for it. Okay, so I'm gonna get the answers, but if you put down the answers when it go through your work, I will grade your exam a lot faster. I don't have to recalculate everything. So we'll recalculate for each questions. If you, so after you've completed the answers for that, so you just fill in the blanks and submit it. So that'll be helping me out, you know, a lot to grade the exam and return it after that. So anyhow. So the today we're going to cover chapter 12. It's pretty much the last chapter. So 5 and 13 will be a small chapter for it. And then it's going to be the main focus for the second exam and the final exam. You'll definitely see this question again on the final. Okay. And on the second exam, the final exam, you can't run away from it. This question is very, very important. So what is it? What is this question about? So this is what we call chapter 12, and then it will be on you know, testing the goodness fit of goodness fit and independent test. Okay, so we have to do like 2 topics for today, so this might be a little bit work for all of us. And if you have a calculator with you, that would be fantastic. It's not going to be really hard for this chapter. But it's going to be pretty complicated in terms of like you have to do multiple calculation at the same time. So for the chapter 12, in this chapter, we're going to test on a single population, okay, for the good and fit test, but we're going to compare multiple proportions. Okay, so the whole idea of this chapter is that we're going to compare. We're going to make multiple proportion, multiple hypothesis. So, okay, on proportion. Okay, does it make sense to us a little bit? So what it means is that we're going to test on a single population, but we have to test every single every single proportions. It's not only a single one, like yes and no. There will be something like 1/3, 1/3, or 1/3. Okay, so it might be a little bit hard to understand what it is. So I'm going to give one example. Let's say we test on the Dye bias, right? So this is going to be like a very important topic to discuss. So you want to know if the dye is biased, if the dye is not biased, or is fair dye is not a fair dye. So it's the only way that we're going to check this is basically we're going to throw in a lot of experiments. So we're going to throw in a lot of like rows, and then we're going to check if the dye lands on number 1, 2, 3, 4, 5, 6. I believe this is a thing that we have done on chapter 6. I show you on the website, and then also in that I test on the 10,000 rows, and then how many dyes that comes up 1, 2, 3, 4, 5, 6, right? And then you're going to record a number of times, and then we compute the probability along the way. If close to 1/6, so I sort of feel like, well, my dye is relatively fair, for instance, but I use the word relatively fair because there's no way that we can prove it. Okay, so it's usually a dye. We can't really make any conclusion about whether or not it's fair or not fair, but we can try to reject as many, you know, as many wrong hypotheses as possible. So we're going to have a better look at the different angle of the statistics. So what it means by that, so test on the dice bias, and in this case that we're going to roll a dice, right? Let's say 100 times only. Okay, so I'm not going to roll too many times because the number is getting really big. And then, so we know the fact that when we roll a single dice, there are actually 3 numbers on it. I'm sorry, 6 number on it. So the sample space that we have, right, will be equal to 1, 2, 3, 4, 5, and 6, correct? Are we good with that? So we have like 6 number on single. Of course, that we can have different numbers on it. So it doesn't necessarily have to be 6, but I just want to make that simple. A fair die is 6. A die is a 6 number on it. So now we're going to work with the website. So this is what we call roll a die. Online is actually pretty straightforward. It's pretty fun. And so we're going to do like 100 times. right? So 6-sided, you can do like 4, it doesn't matter which one. So we want to roll 100 times, and then you want to show statistics only, right? Go. And then this is how it has come up with the results. And then you just want to get the show total, right? And then, oh my goodness, oh, it's still not generated. I'm so sorry. Let's stop. And let me just do that. Oh, what's happening? So let me just do that again. Okay. All right, it doesn't really work out that way. Okay, so let me just do that one more time. I haven't used it for a long time, so I sort of forget it. And let me just deal with the stat. Yes, this is what I want to get, the stat, the final stat right here. So when I roll a die 100 times, I don't remember. I was only like, yeah. Yeah, I would do that. I would do that. No, we do not have class next week. Yeah, I would definitely make it like do on 11:59 p.m. on Sunday. Just want to making sure that we have enough time to solve and to deal with these questions. Okay. Yeah. And for the number of rows that we have, so we just generate a certain numbers, okay, a certain times. So let's say number 1, so we have 12 times it lands on top of the dice, and number 2, there 23 times, and number 3 with 14 times, number 4 13 times, number 5 23 times, number 6 was 15 times. So the total number of rows that we took was 100. Correct? Is that good, people? Right. So that's pretty much straightforward from what we learned, and then we sort of feel like, so this is from the assumption that we make. This is the theoretical hypothesis, and this has to be something that we assume, obviously, that the chains that we can get on 1, right? The chains that we roll on 1 gonna be the same chains as roll on 2, and then it's gonna be the same until 6, right? So this is this is basically 1/6. Are we good? So this is from theoretical assumption, and then we can't prove it. The only thing that we can do statistically, trying to disprove the theoretical assumption. I mean, theoretical hypothesis. Okay, we can disprove things, but we can't prove anything in statistics, because the only number of times that we rolled we just based upon like one single experiment, so we don't really have enough information at all to make a final conclusion on every single case, right? So we only take one sample, and then the majority, the decision that we make, the majority basically on the population by itself. Okay, so this is coming from the hypothesis, so coming from the HO, which is called null hypothesis. Right, so we don't really have this part, okay? But we have to assume that a die is fair before we can disprove it. And then given by the scenario where the first number is 12, the second number is 23, and the third number 14 times, and so on and so forth. So we have to assume from the null hypothesis, which is called term hypothesis, HA. So at least one of them is different. Okay, at least one of them is different. Or we can just say not all of them is the same. It's going to be the same thing as at least one of them is different. So, or we can just say like the opposite for HO. If I can find one of them is not 1/6, and then it has to be a biased die, right? So we're trying to prove that the die is biased based upon this scenario. I mean, this is just a single scenario that I can just change them for some reason, but I'm not going to spend too much time like roll like 100 times, like 10,000 times, or 100,000 times to show up. But the bigger the number that we roll, the more close it is, right, to 1/6. So we knew that before. It's generated system. You can try it out, but I still keep this process. So let's say we're going to go for this, and then you're gonna show the stat, the final stat, for instance. And oh my goodness, it's gonna take forever. And my laptop is lag up for some reason. Show stop. Okay, let me show the stat. It doesn't generate it. Go. Yeah. So it's basically, so if it roll like 10,000 times, it's basically close to 1666, right? And so on and so forth. So the die is gonna generate a lot better when you take a bigger sample. But we're not gonna like spend too much time concerning that. So we're trying to prove this is, you know, like bias, non-biased for that reason. So the thing that we learned from chapter 10, I'm not sure if you guys do remember what it is. So this is basically what we want to test on single proportions, right? And then we're going to use the z-test for one of this. Okay, so I'm going to come back to these questions later on. So the first that we might want to look at will be from the chapter 10 perspective. But and make sure you're not going to do it on the exam like that. Even if you do, I guess still give some partial credit for it, but I feel like this is not like the good way to get it done. And especially we cannot test all of them simultaneously. So it's not going to work out. So we have to test every single one proportions, you know, simultaneously, which is not quite easy at all. So coming from chapter 10 perspective, that we're going to look at the z-test for proportion. So we're going to take the p hat, right? Still remember what it is? Minus the p over the square root of p times 1 minus p over n. Are we good? Yeah. And the n will be 100 times, right? So we roll dice 100 times. So of course that we have to roll for P1, the P hat one, and then the P is going to be the same as actually 1/6. So we don't have to worry about that. And then we can compute the P for the first numbers. So the P, so that'll be 12 over 100, correct? So 12 over 100, which is 0.112. So we can definitely gonna do it by taking 0.112 times minus 0.166, right? So 1/6 is 0.166. Okay, and then we're going to divide it by a certain thing like that. So I don't want to bother myself to do it. Just call it, this is what it is, right? So you're gonna take the square root of 0.166 times 1 minus 0.166 over 100 and take a square for that. And then you definitely going to get this one positive, for instance, right? And because the bottom is positive because it have a square root, the top is positive because it's 0.18, right? And then it's going to generate, no, 0.112 actually, I'm sorry about that. 12 over 100 is 0.112. I do apologize for that. So this one is negative. So let me just change a little bit here. Are we good? And so this one is negative z for that reason. Okay. And then, so this is test for Z1 because we have to look for 6 different proportions. We have like P1, P2, P3, P4, P5, P6, right? And then for the second numbers, it's like 0.23 because 23 over 100 is the P is 0.23 and so on and so forth. And then, yeah, but I'm not gonna care much about the results here. I just put like a lovely answer for that. So, but we definitely gonna have some Z's positive, I'm sorry, Z positive for the second dice, right? For second numbers, because we have, which is for 2, so that was 23 over 100. So 23 over 100 is 0.23, and then minus still 0.166. I just route up to 0.166, right? So you can keep like 1/6 if you want to make it more specific on the hypothesis testing, but I feel like using decimal point is good enough for that reason. And then we're gonna do the same thing, like the bottom is gonna be the same because the same P1 equal to P2 equal to P6, right? So in this case, we're going to have some positive numbers and some negative numbers. So there's no way that we can do all of them at once, right? So we can, so you imagine that. So they have to be at least like 16.6 on average, in order to have something that you know, to be non-biased dies, correct? They have to be a fair die. So each number that we roll should be on average should be 16.6 times. Are we good? But there actually some negative. So 12 going to give us some negative z, 23 going to be some positive z, and 14 will be negative, negative, positive, and negative. So we have like mixed positive and negative z values, and there's no way that we can test it easier with some greater than, some less than. Should we reject the first? Should we accept the latter? Should we reject this third and accept the 4 and 5 and 6? So doing all of this is going to be drastically hard and, you know, intense. So what the statistician they do is the fact that they make another one. So it's just going to be very complex system, right? So this is very complex. Right? And then all the p's that we have to be added to 100% at the end, right? So very complex text doing the z, because we're not going to test for a single one proportion. We have to test for 6 of them, and then we don't know which one's positive and which one's negative, which one is go off the boundaries of the critical value regions, or which one is going to go in the boundary of the critical value region. So it's not quite easy to do it that way. So what the statistician to do, just they going to make the chi-square. The chi-square is, which is called the x square on top of that, and then the bottom will be the degree of freedom. Okay, so the degree of freedom in this case will be equal to c minus 1 or a p minus 1. I just don't want to, you know, get you wrong in this case. So the df is the number of categories. So we have 6 proportions. We're testing on 6. So the C will be equal to 6. We have 6 proportions. Also 6 minus 1 in this case will be the chi-square of degree of freedom equal to 5. Okay. And then it will be computed by the Z1 square plus Z2 square, right? And then up to Zn square. Yeah, this is what the chi-square looks like. So the n has to be the ZC. Okay, C. So we have 6 of them, so we have to add of the square of the 6 Z's together. Yeah. I definitely don't know. We can use different letters. Would you might even use C represent the number of categories, right? A number of proportions. I feel like if it use the letter P, I feel like it's a little bit confusing, because it sort of feel like it is proportions, or it is probability, or it is something else. So I just want to use C just to represent the number of category. So if I give you the question with like 5 proportions, so we know that the C equal to 5, and then we have to look at the chi-square of degree of freedom equal to 4. Yeah, and if you ask me why I use that, I just feel like it's a little easier to do it that way. You can use any number, but just don't use n. So let me tell you why. If you use the number n's right here, you might get confused with the number of time that we took, right? So this is the number of sample. I took 100 sample. I roll a dice 100 times, so n should be 100. So if you get confused with n and p, then we got a lot of trouble. So we never use something really big degree of freedom on the proportion. Okay, so this is regarding the number proportion that we're trying to test. And if you ask me why we have to test on C minus 1 but not C, it's relatively similar to the concept of the t-test, right? So why we have to compute the degree of freedom n minus 1 for a single sample. So usually that we have to do some reactions for, you have to compare the first Z and then the second Z and the second Z, a third and 4, 5, and 6. So we're missing one of them, right? So definitely that we have to take C6 minus 1 equal to 5. Okay, and then the proof that people can actually prove it on the perspective of the P, but regarding the N, and then we do all of that. So the chi-square also be computed by this method. So the chi-square is go to the sum of the observed minus the expected square. Okay, I will let you know what it is. So that would be the observed minus the expected. Oops. Oh my goodness. All right. Have you seen that before? Maybe. Yeah. It's going to check whether or not the test is significant. So yes, so it's gonna be a thing. So what is the E and what is the O? So the O should be given. Okay, so the O will be the number of times that we roll a dice, and then I got all of this, right? So the O will be like 12, 23, 14, 13, 23, 15. All of them have to be given from the questions. What a point of chi-square? The chi-square going to test on multiple proportions at the same time. Okay, so we can't just do like one of them and to check for that. You accept this, you check for that, you reject this, you accept that, you accept. So there's no way they can make that decision simultaneously. So we have to use the test the chi-square, which is the sum of the z-square to test that part. Okay, so this is given from the questions. This is something that we do the experiment. And then the E, what is the E? So this is what we call the expected value. So what do you expect for the number of 1, okay, coming up, right? What is the expected number of 2 coming up? Given that they are the fair dice. So these are the fair numbers on the dice, right? So this is what we call the expected number, okay? Or expected frequency. So I just don't want to, torture your brain and so on and so forth for all of this. Okay, so now we're going to make the chart. So this is generated, it should be the observed, and now we're going to compute the expected. So what is the expected? We call E, okay? If you ask me why we call E, is just expected something, we just started from the first letters, and then it's going to be what? It's going to be, anyone knows? So if I call my die is fair, so the chance I can get a number 1, for instance, will be 1/6. But now I roll 100 times, how many 1 that should come up? Okay, so we're going to take, yes, 16.6. Does it make sense? So you roll a die 100 times. So we assume my dice is fair. So the chance is 1/6, right? So how many times that 1 showed up, right? On top of the die, of course. So we have to be, people, you have to be 16.6, correct? So that'd be 100 times 1/6. That would be 16.6. Are we good? From the assumptions, from the hypothesized perspective, right? So we assume that each of them is 1/6. We test on the independence. I'm sorry, we test on the the proportions, right? So number 1 should be 16.6. Number 2, we're going to do the same thing. So that'd be 100 times 1/6 is 1 as well. So it's always be equal to 1/6 for this case. So that'll also be 16.6, 16.6, 16.6. Are we good? Are we good, people? Yeah, this is what we have from the assumption. So, oh, I have 6 number, but I only have like 5 of them. Would you mind if I make that slow more so you can actually see them? Yeah. Okay. Right? Does it make sense? 1/6, I roll 100 times, so we should expect to get 1 with 16.6 times, around 16.6. I mean, it doesn't make sense like 16.6. What do you mean by that? It should be between like 16 or 17, right? And then for number 2, it also be the same as 16.6. They have the same probability from the assumption. So the expected frequency is actually coming from the from that one, right? From the hypothesis, and so on and so forth. Are we good? Are we good with that? And then, would you like to use a charge computed? So we have the observe. So this is the observe, right? This is the observe. This is what we have for the expected. And then we have to subtract them, square it, and divide it by the expected. Okay, does it make sense? Would you mind me? Would you like to make a chart like that, or we just want to make, just write up the forms and that's pretty much it? Okay, so let me show you how. All right, so let me just do with this question. So first, I'm going to take the observe, what was 12, minus 16.6 square over 16.6. Are we good? So let me just repeat that again. So this one, the observe will be 12, right? And then the expected 16.6 square and divided by 16.6. So all we have to divide it by the expected, okay? Observe, and this is expected. And this is also the expected. Right here, coming from observe, coming from my system, from my calc, from that one. Yeah. I got rid of it. I'm so sorry. It should be, yeah, it's right here, coming from right here. After we roll it like 100 times, this should be given a question. This is what we do it on the website. Okay, it's coming from when you roll a die. Experimentally, this is what we have for 100 times, bro. Yeah. Isn't the fib was 23? Yeah, 23. I mean, they can't be the same number. I just don't know. It's coming from the system. So 523. Yes. 523. So the observer 23, that makes sense. Are we good? And then we just keep adding this. No, you start with the first one. We have to add up all of them, right? So the first one was 12, so I have to use 12. And then the second one was 23, so I have to use 23. Oh, we have to do every single one of them. We're not going to do the fifth only. We have to do every single case. Remember the chi-square test? We have to test all of that simultaneously. You have to do every single case. You cannot just leave one of them untested. You have to do for every single proportion within a single population. Okay, so we have to do all of them within a single population. So now we're going to do the same thing for 23. Are we good? So I'm going to change the mark a little bit. Just want to make sure that we understand to subtract 16.6. And then we're going to do the square. And also we divide it by 16.6. Is that good, people? Is that good? And then we're going to do the same thing for 14. And then square. I'm sorry, minus 16.6 square and divided by 16.6. Yeah. You know how many times I have to do that? How many of you would like to make a chart? So first I'm going to subtract them. I take this, subtract this, and square it. And then next I divide it by all of this, divided by 16.6. I feel like it's a little easier if you want to do it that way. You just do, like one of them separately. So let's say I'm going to take like this. I'm going to do like this, observe minus the expected and square over the expected, right? And then we just do one single calculation right here. Instead of we just do all of that once. It's up to you. So it's right up to you for that. 16.6 plus dot dot dot. Can I just put dot dot dot? Do we understand that part? So we have to do the last one with 15 minus 16.6 square. It's just like a lot of calculation at once. So it's not something really horrible, but just when it comes to computing all of this, it's not quite easy. And because we have to do 6 of them. Remember, if we give you 100 proportion, how many calculations do you have to do? 100 of them. If that's not possible, I would say I would give you at most 4, at most 5 proportions. Right? I can't ask you like 20 proportions, like each of them with 5% chance. Making so many categories, that's gonna be so crazy to compute all of this. Right? So we have to do every single one of them. So it can do that. It can do like on a calculator. I'm not sure which way is going to be better, but some of my people prefer making a chart, because making a chart, you never make mistakes on. You do one of them, right? So we take 12 minus 16.6 square over 16.6. And then we got the answer is 1.275, right? Are we good? And then we keep doing that. Oh, what you mean is happening whenever. Yeah, I'm gonna give you like RIP after the second exam. That's gonna be a lot. Yeah, we cannot. You cannot put like RIP on the exam questions for the answers. No, I'm gonna give you much credit for that though. And then we can do the same thing for the second ones, and then we gotta take like 23 minus 16.6, and then square over 16.6. And then we got the answers with 2.467, right? Are we good with that? How long does it take? It should take long because we have to do like 6 of them. Is that good, people? And then we're gonna compute all of that, and then you take a total, right? Take a total. Okay, are we good? Do you like a chart? Obviously, if you don't like a chart, we can just do all of them at once. So I'm gonna do like 12 minus 16.6 square plus, I know I have to divide all of them by 16.6, so I just plus 23 minus 16.6 square plus, because they have the same denominator, but usually they don't. And so, and then we do the third, that will 14 minus 16.6 square plus 14, 13, 23, 15, right? So 13. Can somebody help? Oh, come on. You can't just let me suffer. You have to help me. Remember, I'm the one who graded exams. So if you don't help me, who will? Okay. You should make me happy before we take the test, right? Correct? So if you make me suffer for all of this calculation, I will make you suffer on the exam. So that's not fair. Correct? And have to divide it by a total of 16.6. So we got the answers was 7.5518. Is that good, people? Is that good? Yes. Marvin is like, it's really good. Yeah, everybody just like that is like, as long as it gives you some good grades and be like, oh, he's actually one of the best, whatever it is. But it's not true. Sometimes understanding something that we're doing and take care of certain questions, a certain issue that you have, it takes a long time. I believe, yes. It took me so long to do all of this. How long does this take? Don't tell me like 20 hours for that question. So the answer for that was 7.5518. Are we good with that? Is that good? Okay. Yes. So this is the thing that we compute the chi-square, and of course you can do each of them separately. You can take you can do this. You're gonna get that, and then you can do this. You're gonna get that. You can do this, and then you're gonna get that. and so on and so forth. You can do like you can just break it down into 6 different computations, and then we just add them up. So when you add them up, you should get the same answers as 7.552. Which way is better? Some of my guys said, you don't have to. The exam like, I might ask you to route up to 2 decimal number, right? It just route to 2 decimal number. I'm gonna give you full credit for it. Okay, full credit for that. And yeah, if you can give me 3, so that would be better. But I feel like 3 should be okay, or 2 should be okay. Okay, but you're just not gonna give me like 7.55180788282 or something like that, because when I look at this number, I'll be very busy. You know, when I get busy, my grading skill will be worse when I grade the exam. So what does that mean? It's going to be a things right here when you test on. So the chi-square test is going to be something like we have like a mountain, but it's not like a mountain at all. It's like, it's not a symmetrical mountain compared to the t-score, and it's started from the right. Okay, and then so this is what we call the chi-square test. If you sort of look at the charts under the table, okay, this is the chart that we're looking for. Oh my goodness, we downloaded 5 times. I think 20 times. I got rid of so many times that we downloaded. Yeah, this is what the chi-square test looks like, and then this is going to give us a chart. So assuming that we test on 5%, right? So use alpha equal to 5%. I mean, it's fair to use alpha equal to 5%, meaning that we're not taking so much risk. We only take 5% risk. I feel like it's a very, very affordable. Okay, but if you take the alpha equal to 20%, I would say, well, it's not good at all. I mean, because if you take alpha really big for that, so the chance that we make an error, that the test, the hypothesis, the analysis might not be very valid, because we're facing like 20% risk. That's huge. It's just like when you tell me that when you take this vaccination, you're facing like 20% risk of getting infected. You'll be like, no, heck no, I'm not going to do it. Yeah, it's the same concept right here. It's just not going to be safe in terms of that. Yes, it's always be given. If the alpha is not given, always take 5%. It's at the very standard level that most statisticians they need to use. So the alpha is going to be given from the questions to look for the critical value of the chi-square. So we're gonna go for critical value C. So the alpha was 5%, and then the degree of freedom equal to 5. So what we have to do, we're gonna go all the way down to the last chart. Okay, so you guys see that? And then I'm going to copy down this. So 5%, correct? Is that good? And what is the number that you see? So the first that we're gonna go to degree of freedom equal to 5, and the second that we're gonna go for 5%. Is that good, people? Yes. And then the value that we found on the chart is 11.07. Is that good? So now this is what we have for the critical value. So assuming that we learn it, this is just my assumption, right? So we learn it. So the testing value that we have was 11.07, right? So if the values go here, I mean, if the value is 7.552 is going here, that we're going to say good, that is biased. So so we're going to accept the eternal hypothesis, right? So, but if the value just going inside of it, right? So apparently that we have 7.5 here, and let's go inside of the undecisive regions. So what that means is that we go into reject xj. Is that good, people?
Wait, can you repeat that? Of the chi-square values false. What do you mean?
Yeah, for out on the right of 11.07, we go into ecstatic J, saying that the die is the bias dice. But if the number is for into it, for into the mountains, okay, just for into the mountains, this is what we have right here. So what's going on for that? We go into fall within the indecisive region, so we cannot accept xj. We're going to reject xj, and then we're going to say that we cannot disprove that the die is biased, but it doesn't necessarily mean that the die is fair die. Just want to make sure. I just want to make sure that we can prove anything in statistics. The only thing we can do is just trying to reject the hypothesized assumption. Okay, so this is the thing that we deal with. Is that clear, people? So in other words, if we have the chi-square of 5, okay, less than. So less than have to be inside, right? Less than have to be the inside of it. It's going to give us what? We're going to reject. If the chi-square 5 less than the critical values, then we're going to accept xj. Are we good with that, people? Oh my goodness, I always have
just to clear up, the second part represents the critical value and the first part represents the value of chi-square.
Exactly, something that we computed from the from these pictures from the website, from that one. Yeah, from the picture we just posted. Yeah, so this is that we computed from a sample, right? From 100 times that we roll dice, and this is what we have from the assumptions. And then apparently that our sample is not generating some biased results. Okay, so in other words, we're going to say that my die, no, we cannot say that my die is biased. That's it. Okay. Which table number is this? I would say I don't really have the chart numbers right here. What I can show you is basically on the last one. Okay, there's no number for it. I'm so sorry. It should be like 811, but it doesn't really have even the numbers on that page. The chi-square being isolated by itself, I don't know what's happening with this. Okay, I would just say it's basically going to give you like the chi-square distribution chart, and it's going to give you like a lot of degree of freedom, but we only use usually the first one. Okay, the first chart. It's not going to go like down to like 100 and whatever it is. You're not going to get like 100 proportion. That's going to be a crazy calculation. You should get at most 5 or 6. Okay, I would say at most 5. 6 still be really hard to compute all of this, right? The calculation was wrong. People get tired and they couldn't do well on the exam. They blame on the question. No, because the question being too long. And then you use 3-letter words RIP on the exam, which is not cool. Yes, question.
What if it was equal to?
Usually it's not equal to. It's very rare that we're gonna have like an equal signs. Like you can't really compute exactly like 11.07 coming from all of these values. It should be slightly less or should be slightly greater than. Okay, so it's just certain. It's just like it's just when you compute the probability of the of continuous model. So the probability of a single point will be 0. So it's like a very small, but we can't compute it, so it has to be equal to 0 for that. So there's no chance they're gonna get the exact same value like this on the exam. Okay, so either it has to be like very close, but it cannot be exactly the same. Are we good? Okay. This chart matters. So we understand the fact that the E will be computed by N times PI, right? So so the I will be a number of categories, right? So I1, I2, I3, I4, I6. Yeah, perfect. How many of you want to use a chart? I feel like using a chart is easier to compute all of this, but unless they have a same denominator, so you sort of feel like, well, it's easier. But if they do not have the same denominator, you have to do one by one. I feel like it's a little better for that reason. So let me just check out using with another questions on the chart, and let's see. Okay, let's see. This is the classwork questions. I'm not going to do it. I'm going to do some Mendel laws. How many of you have heard of that? Like, we have dominant genes, we have hidden genes, something like that. Yes, C will be number proportional. Let me just do that. Proportion. Yeah. It can be confusing. Exactly. So that's the reason why I have to use C. I cannot use N. If I use N, you'd be like, what? N equals to 100. So we have to look at 100 degree of freedom. No, we only look at like a small degree of freedom. Okay. Let me just go for this question and see what's going on. Okay. Okay, so this is given from 4 proportional test cards, so you don't have to do like so many calculations for that. And then the Mendel's law is, you know what it is, right? So now we're 16, you know what it is, right? So we have so we have one gene coming from the dad, one gene coming from mommy, and then so the dominant gene is gonna be 3 over 4, right? Still remember what it is, and then there have to be 3 over 4. You multiply them, so that'll be 9 over 16. Did you take any biology course before? And then this is 3 over 16, and then this is 1 over. So this is 1 over 4 times 1 over 4. Is that good? Oh, come on! You don't know what it is? Shame on you! This is coming from the Mendel's laws. This is one of the very famous laws before from biology. Okay, so we have 4 different phenotypes. The one tall cut leaf, and one is tall potato leaf, and one drop cut leaf, and the other one drop potato leaf. So all of this given by that example. So now we're going to rewrite the null hypothesis, correct? So we're going to get HO and H1. Are we good? So the HO parts that we have going to be P1 equal to 9 over 16, and P2 equal to 3 over 16. Are we good with that? P3 equal to 3 over 16, and P4 equal to 1 over 16. Is that good? And then you're going to say at least one of them is different. Oh, you can just say not all of them are all the same, so it's going to be the same thing. Any concern for that, for the hypothesis that we have? You have to write down the hypothesis, so this is part of the grade. So don't skip this, okay? Make sure that you're going to do for HO and H1 on the exam, no matter what. Are we good? Are we good with this? No. Okay, so now we're going to so we're going to compute the expected numbers, right? So we have to compute the expected number for the first one. How do you know? No. How do you know that one of them is different? Because we test on a population, even if the samples should be different. The sample should be different, of course. So when you compute expected, okay, so the expected values for the first one will be equal to n times P1. Are we good? Are we good? So can somebody help me compute the n, the total for all of this? Oh, come on. Can somebody help? Okay, I try. 1, 6, 11. Very good. So we got 1, 6, 11. We add them up together. And then, so from the assumption, we should expect to get how many tall cut leaf right here. So we're gonna take 1,611 times 9 over 36. I'm sorry, 9 over 16. I apologize. So 9 over 16. So we should expect to get how many of them? Expected from the Mendel's law. So we're going to take 1,611 times 9 over 16. We should expect to get 906. Are we good? Oh, come on, just give me 906 in this case when a number getting big. When a number we're getting like 1,000, something close to 1,000, and you just give me, the whole number for that. It's something that we have close to, like 16 something. So you're gonna keep me one decimal number. Other than that, just leave the answers with the whole numbers, and then you add up later on. Are we good? Okay, so we're gonna compute the E2 as well. So the E2 will be, yes, 302 very fast. What about only one person helping? What about the other people? Come on, guys. Oh my goodness, I know the semester was challenging. It was almost like going towards the last part of the semester. So we're gonna go for 3 over 16. So we're gonna get 302, and the third one's gonna be the same, right? So the third one's gonna be also 3 over 16. So you have the same proportion. So the answer should be the same. And then for E3, so we are supposed to be n times P3. And 611 times 3 over 16. So it's going to be the same as 302. And then the last one is, yeah. The last one is 100.7. It should be right up to we should round up to 101s. Let me tell you what, if you just only keep 100, so when you add them up, they do not add up to 1,611, right? It doesn't really add up to 1,611. So we have to keep E4 slightly above 100 because we already route down for all of these values. So we have to route up for that reason. So I just take 1,611 minus 906 plus 302 and 302. Is that good, people? Instead of doing the math, I believe doing this will be a little bit faster, so we get 101. Any concern? Any question? Any questions so far? Is that good? Yeah. Wait, you'd be like, why should we route up for that one? Because you want to add, so when you add them up, the total number of the expected have to be equal to the observed. They have to be equal to 1,600. This is the number of sample we took. And all of a sudden we have adding up all the expected numbers and then got the answer, which is 16 and 10. So we're missing one of them. Where does it go, right? So we got 101s here, okay? Yeah, but it's slightly, so we need to take 1,611 times 1 over 16. So we have the answer should be 100.7, but you have to add up a little bit, right? So you take 101. Is that good? All right, so it's not a big deal at all. So now we're going to compute the expected values. So the chi-square statistics. So this is what degree of freedom. So we have 4 categories. So the DF equal to 4 minus 1. So that would be equal to 3. Are we good? Are we good with that? The chi-square of 3. Okay, and then we're going to take the expected, so we get 926 minus 906 square over 906. Are we good? Are we good with that? And then we're going to do the same thing as well. So therefore, this should be okay to compute it. And then we're going to take instead of 906, so we have 288. So remember, all of these are observed. So the questions should be giving us the observed frequency. And then the computed will be the expected frequency, right? And then don't mess them up. Don't mess them up on the exams. So now we're going to take, would it be square? Yeah, this is a square. I know I have a handwriting getting worse. So this one is square right here. Okay. Yeah. And then we're going to take 288 from the observed minus the expected. So the expected was 302. And then you're going to square it. And then we divide it by 302. Are we good with that? Are we good with that, people? And then we're going to do the same thing for the third one. So that'll be, so the observed was 293 minus 302 square over 302 as well. Yep. Are we good? And then the last one was 101 minus 104 minus 101. And then square it and divide it by 101. Okay. Any concern for that? No, it doesn't necessarily have to be rounding up for that reason, but when we computed the expected number, you can either round up or round down, it doesn't matter to me. But the thing is, they have to add up to like the total number of sample. The sample that we had was 1611, right? 11 is my favorite number. And then we, of course, when you compute the total number of the expected numbers, it have to be equal to 1611 as well. So when you round down for 3 of this, we should round up for the last one. Just want to make sure that they do add up to the number of sample size. Okay, so when we compute it, and is that good? Or yes? Oh, come on, you guys, really fast. I love it. So the answer was 1.447. Are we good with this? Oh my goodness, you guys get making me so proud for computing the expected numbers. So we can't do it like all of them at once. So we can take 926 minus 906 squared and divide it by 906, right? I know it should be the correct calculation. I just want to show you how you're going to do it here. Square over 302 plus the third one, 293 is correct. 293 minus 302 squared over 302 plus the last one was 104 minus 101 squared over 101. So we should get 1.4. Oh, now you got something. It doesn't match. Okay, that makes no sense. What's happening today? Okay, let me just do that one more time. Oh, you gotta be kidding me. So how is that even possible? I couldn't really compute this one. Every single time, I don't know what's happening with this. Oh, it was, I think I'm missing one plus here. Go. Oh my goodness, yeah. My dog is like it's a Pomeranians, but so it's a little bit when there's actually the guests coming in, so it's keep walking for that reason. This is happening for that. So I'm trying to check if the calculator's here working out, but it doesn't give me the final answers. Okay. Yeah. Oh yeah, I know, but what I'm saying, so I don't know what's happening. It looks like there's an error. Oh yes, GoGo is dumb. It's actually really, how is that even possible? So I think I did everything all right, except for I'm missing twos right here. Yeah, no way I'm missing right now. Now I got 1.447, so we just double check we're missing the square. So the square is like missing the twos here, so I got 1.447. So that's pretty good. So now we're gonna go for the next part that we need to look for the critical value for the chi-square, and then it has to be equal to degree of freedom, 3 degree of freedom, because we're looking at 4 proportions. Now we're going to go for chart table number 12. So the answers for the critical value was, is that 5%? So 1%. So we're going to use the alpha with 1%, right? So in this case, you know, look at the alpha as 1%. And the chi-square of 1 is going to give us, let me just copy this real quick. We have enough space for that questions. Okay, so the chi-square of 1, which is 0.010, and then we're going to go for 3. And the answers for that would be 11.345. Is that good? Any question? So apparently that we have the chi-square of 3. Yeah, if this number is very small, what's happening? Because the difference of the observed and the expected is not that big. So the Mendel laws should be okay for this phenotypes. Okay, so in other words, we have the chi-square of 3 less than the chi-square of the critical value for sure, right? So we're going to reject HA. How we good? I mean, the Mendel laws still work properly, but we can't approve it. We only reject if it go against it. Okay, so it basically means that we're going to reject and fail to reject HO. Any other concern? Any questions? Yeah. Okay, so I hope that this is okay for all of you. And of course, you don't have to show me work on a chart. Just write up the numbers with the chi-square of 3 and the alpha at 1%. Okay, so remember, the degree of freedom is not equal to n-1. It will be the number of categories minus 1 for the chi-square test. Okay, so that's going to be the part that we're looking for. Any other concern? Any question? Yeah. We don't know if there is one of them. It can't be 2, it can be 3, it can be all of them, right? But if one of them is wrong, at least one of them is wrong, so the Mendel law should not work. Okay, so this is what it means by at least one of them is different. And you can also use another word when you write down the eternal hypothesis. So we can also use none of them are the same as HO. I mean, not all of them are the same as HO. So we can also write that to write up the eternal hypothesis, but I feel it's not really matter that much to us. Exactly. So what it means by that is we do not have enough evidence to reject the Mendel's laws. So this is what we going to write up right here. Okay, so we can't not claim that it go against it. Okay, it is not consistent with Mendel laws. That doesn't make sense. Does it make sense for us? Are we good? Yes. So I have an English during my class and then on Monday, Wednesday class, and it asked her like, is that going to be the same to say we cannot claim it is not consistent? Is this going to be the same as we claim that it is consistent with the Mendel's law? So the answer is no. Okay, so the answer is no. So it's like we have double negation is going to be the same thing as the whole thing. So you can't just say we claim that it is consistent with the Mendel laws, but it's actually not happening in statistics. Okay, we cannot reject it. I'm sorry, we cannot reject it. Doesn't necessarily that we going to accept it. So this is just like way confusing, but it's actually just want to making sure that there's no way can prove any null hypothesis in this case. Okay, so basically, so this is going to be the things that we say, okay, I don't think it's not consistent. That's it. I don't think it's not, I don't think it's going against it. And I feel like that's pretty cool to say that though. Okay. So I believe this is going to be the whole thing, but it doesn't mean that we're going to accept this guy, right? So this is good. This is the Mendel rule. It should work for most of the, biological perspective, but it's not going to be working out because the sample that we took is 1,611. So that is not good enough to just say that Mendel law is correct. But we have good enough information to say that, this is not true. All right, so now we're going to go to the next part of chapter 12. Are you ready to take the next one? So this is 12.2. So cover this. So 2 of these questions going to be on second exam. So you should expect to get those questions. So one of them that you're going to see multiple proportions, right? So you might see something like that, like M1, 2, 3, and 4, okay? So, and then all we need to do just computing the expected numbers, and then we do the chi-square, you use the chart, and make sure that you look it up with the correct degree of freedoms and with the alpha. The alpha is 1%, so we have to go from the right to the left because chi-square is going from the right. It's positive. There's no negative value for chi-square, and then we're gonna look through the degree of freedom and look for the right values. And finally, if the chi-square less than, so we're going to reject. If the chi-square greater than, we're going to accept xj, right? So when you reject xj, meaning that you fail to reject xj. Okay, so that's going to be the entire story of 11.1. Are we good? So now it's when it comes to 12.2. So this is going to be a different topic, and it's going to be working out with independent test. Okay, the statement is not correct. It's not correct. Okay. No, the questions should state that are the data from this experiment inconsistent? I feel like this question missing the letter I am inconsistent with the Mendel laws. So then it's still, so that would be the wrongs for that reason. Okay. So the question is asking us, are the data from this experiment inconsistent with the Mendel laws or not consistent with the Mendel laws? The answer is no. Okay. Exactly. I thought that was a chapter 12. I mean, chapter 12 is not that only one part of it. It's just chapter 12, there are actually 2 parts of them. So one of them is test for proportions, multiple proportions. And the second one will be the independent test. Okay, so that's will be the things that we focus on as well. So the independent test is going to be coming from, let me just take one example from the note and from the homework and show you what it is. It's going to be pretty much the same thing when we test on the hypothesis. Okay, so let me just go to chapter 12.2. All right, and this is, I feel like this is the question that we love to test on. Let's go for it. Okay, let's go for it. And and then we're gonna do the next questions later on. So this is the question that we have from the classwork. Suppose that the data classify each person's random sample of 48 students and male students and 91 female students. Okay, so we're gonna have this information. And I want us to remember what we have done before, like we test for independence. So how can we test for that? Still remember the question like that on the third exam. It's been a long time ago, I know it. And we need to look for the total, and then we check if something's happened. If this is not happening, then we're going to say it is not independence, or it is something that working along with it, right? And something like that. Usually they're not independent. Yeah, the PA equal to PA given B, actually something that we have seen it. And of course, the first step that you have to look for the total of the row and the columns, right? So this is a total of, I know my drawing is really bad. I should draw with a different marker. So this is a total, and this is a total. Yeah, so how many of you actually eat 3 meals a day? I don't think so. I'm like 2, and maybe at most 2. Yeah, I rarely eat 3 of them unless I'm on vacations, sort of like, you know, doing something too much for that. Let's say hike the mountains or camping the mountains. So it's I have to eat more to get more calories, but generally 2 meals should be good for me. And we have 26 people, 26 male who eat 3 meals a day, and then 22 male eat 3 meal, less than 3 meal a day, and then female was 37, and then it was 54, actually pretty huge. So for the total number of people who eat 3 meals a day will be 63. Are we good? The total number of people who rarely eat 3 meals a day, I mean 2 or less, so that should be 76. Are we good? Is that good, people? Yeah. Oh, how did you get that part? So 48, 91, and then we're gonna get 48 here. The total number of male and female was 91. And the same thing for the total number of total. So total will be unchanged no matter what. So total should be 139. Are we good? Yeah. So this will be the total number of people, right? Under this painful experience. So now we're going to write up the hypothesis, right? So remember the last class that we have done? Not the last one. I mean, a long time ago, we cannot prove that they are independent. So the only thing that we're trying to do was we're trying to show that they are dependent. Okay, this is what we're trying to show it, and it's coming from the XJ. So the top part, so we're gonna write them down. They are independent. So this is coming from the perspective, from the concept, from the hypothesis, right? And theoretically, that's correct, but usually it's not true. So the second part, we're going to say they are dependent. Are we good? So this is what we're trying to disprove so that we can get their dependence. And let's see if we can do it that way. And still remember from a very long time ago, I'm not saying last class, that we're going to use this concept, right? A given B equal to P of 8, right? So if B has no connection with 8, so the information of B should be irrelevant. So what we have going to be P of A given B. So this one doesn't matter. We can just cross them out completely, right? And something like that. Are we good? So, but doing that might be a little bit hard, because if we look at the ratio of P of A given B, so let's say we look at the male and then the people who usually eat 3 meals a day, right? Given by that, so we have 26 over 63, and then P of A should be 26 over 139. So it might be a little bit tough to do it that way. So another form that we're going to rely upon will be A and B equal to P of A times the P of B, right? Conceptually, this is what we're going to have, right? Conceptually, if they're independent. But of course, we know they're not independent, but by concept, this is what they got. Are we good? Are we good with this? Yeah. So we're gonna utilize this information to compute the expected values. Okay, so now we're going to look at the expected number of males. So let me just go for it real quick. Okay, so now we're going to look for the P of A and B. Anyone knows? So let's look at the first box right there. So I look at 26. How can I compute? Look at the male and the people usually eat 3 meals a day, right? So the n is going to be 26 over 139. Are we good? How did we know to make the null hypothesis? Yes, because the question states that we're going to test the relevance if 2 categories not the same. So it's like a cost, the cost chart. So there's no way that can test for 2 by 2 category using the definition of proportion. So we have the cost tab tables, meaning that we need to go for the independent test. So just want to make sure that the ratio is not going to be the same. Okay, so does it make sense a little bit? Because this is like, there's no way you can get the ratio correctly. The ratio is going to be the probabilities right here, proportion generally. So it's going to be defined for the cost tab table. This is what we call a cost tab table. Okay, and it's another word for that, we contingency chart. Yeah. Oh. Okay. It worked for that. So whenever you see like 2 by 2, it's or 3 by 3, and there's something that we have right here, that's going to be the test for independence. So now we're going to look at the probability of A and B. So we're going to look at the first box. So this is the box that we're looking at. So 26 is the absurd, right? Because all of these values was given by the chart, right? The people who say yes and no. And of course, the number of people who participated for that surveys would not be changed. Okay, I will show you why. And of course, the people of P of A and B will be 26 over what? Over 139. Are we good? Right, we want to check if P of A and B, is that going to be equal to the P of A was 48 over 139. Is that good? Oh yeah, I feel like that's gonna be a lot better. So now we're gonna check on the first columns and the first row. So in this case, that we're going to take on the number of male and eat 3 meals a day, right? Is that good? So we're going to look for A. So A is going to be the male, and then B is going to be eat 3 meals a day. So the number of males should be 48 over 139. Is that good? Oh, come on. Give me some human reaction. I mean, I can't even see you guys doing something. You're just having class on Zoom, and this definitely not going to be working out really well. And then multiply by this over 139, correct? So over times 63 over 139. Is that good, people? Yeah. No, I'm going to show you one case, and then well, we have to do every single box. It's because we test on the multiple charts, right? You have to do this box 26, and then you have to do this one as well, right? And you have to do this one 37, and then 54. Okay, all of them should be taken into account. Okay, hold on a second. Okay, so this is what we're going to deal with. Are we good? And then I multiply both sides by 139. Can I get rid of 139 here? Can I get rid of 139 here? Are we good? Is that good, people? I can multiply both sides by 139. And then do you observe it? So do you believe this is going to be, so this is the observe. Are we good? 26 should be the number of people who got tested by eating 3 meals a day, right? And then this is going to be the expected. Let me just draw out the fractions here. Right. Are we good? Can somebody help me do this math real quick? 48 times 63 over 139. So, and then what do you get? $21.75. Are we good with this? Yeah, so this is what we call the expected. So do you believe that they are the same thing? Of course not. So if they're not the same, so remember the last exam that we did, if they're not the same thing, we're going to say, well, they're not independent, correct? We test for a single box, remember? Right? If they're not the same, so we're going to say they're not independent. But how do you know? Because we need to check every single one of them. We are going to test if the habit of eating and the genders going to independent of each other, right? So it's checking one box is not good enough, so I need to check the second one. So remember that when we look at the ratio, so we're going to take 48 times 63 over 139. Are we good? We take the total number of the rows times the total number of the columns, and then we divide it by n. So the expected numbers for the chi-square, so will be equal to what? So that'll be the total number of rows times the columns, right? Yes, questions?
Yeah, I don't understand why are we multiplying it like that? Why can't we simply do 26 divided by 139 and that gives 0.18 and that does not equal to 0.15?
No, I have my own reason for that. So if you only taking the proportion, it will be really, really complicated. I mean, you can definitely gonna do like 26 over 139 and get a certain ratio, but I don't want to do like so many ratio at the same time. It's gonna be like very, very headache. So what I'm trying to do, I'm going to compute the expected number if they are independents. So if gender and habit of eating are independents, they should generate 21.75 on the first box, on the first row and the first column, right? But they're not, because the observed number of people with male eating 3 meals a day is 26. It should be different with 21.75. But we have to check every one of them. We cannot just check a single box and then you leave the answer like that. So it means that we're going to make another column for that, okay? So this is also like 3 by 3. So I call this is male. Can I do the M? And then the bottom one we call, don't tell me this is Irish, right? This is basically female. And then the total number on the bottoms should not be changed, right? So the total should still be unchanged. Remember the number of men that we collect was, hold on a second, let me just show this. Okay, so is that good? Does it look good? Okay, so the total number of male was 48, right? Are we good? And the total number of female was 91, so it's still being changed for that reason. And then the total number of people who under the survey was 139. And the total number of people who eat 3 meals a day was 63, still being changed, right? So those numbers will not be changed for sure. Remember, the totals of each will not be changing. We can't change the fact that there are 48 male and 91 females in the group. and then sick people eat 3 meals a day, and some sick people eat less than 2 meals a day, right? Or less than 3 meals a day. So this is what we have for the value. Are we good? Are we good with that? Okay. Yes. So now I'm going to fill in the first ones. The first box that we computed by taking 48, right? So we can do the math by taking 48 times 63 over 139. Are we good? So I got the answer, which is 21.75. Any concern? Any concern for that? People? No. May you repeat? So I'm going to take, so in order to get the first box, I have to take a total number of males. So I have to take the column totals, right? So this is on the first row and then the first column, right? So I have to take the total number of the first row times the total number of the columns of the first column, and then be divided by n. So I get 21.75. All right, so I need someone else to help me compute the rest of them. How can I get this box, people? How can I get this? Oh, come on. How can I get this? Anyone? You're gonna take 63 minus 21.75, right? And then exactly. Okay. Yeah. So we get 41.25. How we go with this? Okay. Is that good? Is that good, people? How can I get this one? Yeah, we take oh, what you gonna take 48 times this? Oh no, I'm not gonna do it that way. Yeah, we can just subtract them. If you take 48 times 76 over 139, you should get the same thing, but it's 48 times 76 over 139. Yeah, we should get the same 26.25 actually, just like it different. Yeah, that's fine. It's happening. The finger problems. Just a little bit, just a little things to work with that. And oh my goodness, I'm getting this really small box. I didn't expect that. It's like getting too small. And then the bottom part, we're going to take 91s, or you can take 76 minus 26.25, right? So we're going to get 49.75. Are we good, people? Is that good? Is that good, people? Yeah.
So basically you did 76 times 91 divided by 1.
Yeah, we do the first one and get the rest. We get the rest of them. If they give you like 3 by 2, we do the first 2, we get the rest of them, right? If I give you 3 by 3, oh my goodness, if we give you 3 by 3, it's gonna get like 1, 2, 3, 4, 5, 6, 7. I'm not gonna do that. If I give you 3 by 3 box, you just say, I give up this question, just too much for you. You're gonna do 6 and 9 calculation. Remember that each one you're gonna be 1 observed, 1 expected, 1 observed, 1 expected. You have to do like 9 of this. Imagine that you have to do 9 of this on the exam. Would be like, are you serious for each question? That's too much. Yeah. So I'm going to, I would say the most difficult part would be 3 by 2 chart. Okay, 2 by 2 should be good. Like you do one of them, you can fill in the rest of the parts. I mean, you can do like the bottom one by taking 91 times 63 over 139 as well. It's up to you. So now we're gonna do the chi-square things, right? So the chi-square. So the degree of freedom is no longer equal to rho minus 1 because we have the cost tab table, so they are irrelevant. to each other. So we came to just like taking like all of these columns and multiply by the row. So that's what we so we have to take away one of them. So right, so we're gonna take the column minus 1 times the row minus 1. So the column that I would give you, I give was 2 columns, right, and 2 rows. So that'd be 2 minus 1 and 2 minus 1. And the degree of freedom that we have to look for is 1, right? So very likely, on the exam, I'm gonna give you degree of freedom equal to 1 or 2. That's it. It cannot go that far. It cannot go that far. So the chi-square of 1 would be equal to what? The R would be the row. So I give you 2 rows and 2 columns. So this is the things. So this is the rows and this is the column. Okay, 2 by 2. So look at 1 degree of freedom, as symbol said. So if I give you 3 rows, 2 columns, so that'd be 2 minus 1 times 3 minus 1. So that's going to be 2 degree of freedoms. At most 2. I'm not going to give you 3 by 3. It's just like too much calculation for that reason. So now we need to compute the chi-square. So we have to take the observed, right? The observed that we have done so far, the observed with 26. Are we good? And subtract the expected. So the expect was 21.75, right? This is what we computed. And then you take the square and then over 21.25 is all we have to divide it by the expected. So just making sure that we get the forms correctly. So always be like observed minus the expected square over the expected. I mean, the top part, it doesn't matter which one that you subtract, because when you square, you should get the same answers. But when you divide it, you have to divide it by the expected. So this is a thing that I have for the formula. So now we're gonna do the rest of the box. So we have to do 1 by 1. So okay, so after the first one, you can do the second one, which is 22 minus it's 26.25, right? And then you're gonna square this part. Correct. So I'm trying to recall, just want to make sure that we, we're using expected and the observed for those twos, and then we divide it by 26.75. Are we good with that? Okay.
Wait, for the degree of freedom, right?
Yeah.
You're only counting the columns where like the numbers are at, right?
So we have 2 columns, 2 rows, right? 2 column. So this is 2 row and 2 columns, correct? 1, 2. Is that good?
Yeah, but what if the data was not given in the table?
The data have to give you in a table. Then you can say, well, the data is not here, so how can I do the exam? The question must give us the data. This is the observed numbers, and then from a data set, you're going to use the total to compute the expected, and you subtract something, it's add something for that reason. Yeah, was it 26.25? Oh yeah, I have some eyes problem. Before the break with Thanksgiving, I have a lot of problem with this. Yeah, it's a little typo for that reason. I'm so sorry. It's a 26.25. Yeah, I have some eyes problem. Yeah.
So you would have to do the next ones, like 37 minus 41.25 squared.
Square, and then you divide it by 41.25. That's correct. So we have to take this box, subtract this, next, subtract next. You can't just take like that one and then subtract this one. So it makes no sense, correct? So we have to take the corresponding box and subtract them and square it, and then you divide it by the expected. And then we should be able to get the final answers. Okay. Oh, come on. And now we're going to, can somebody help me do the math for that reason? I put that up. I'm running out of space for that reason. So can somebody help me do the rest of that? Got you. Oh, come on, give me some hopes before before the exams. Musical artist, it looks really cool. Look at your face. So we take 26 point minus 21.75 square plus divided by 21.75. What about the rest of what about the other people? Come on, I thought you guys active. Please help me out. You don't want to make me suffer before the exam. I will remember your names at the end of semester. Right? Correct? I'm calculating. It's a lot. I know it's a lot. So let me just do that. 37 minus 41.25 square minus 41.25 square over 41.25 plus 54 minus 49. I just want to make sure I'm not missing any parentheses or any square or something like that. It will be uncalculable. So 54 minus 49.75 and then square over 49.75. Okay, that's it. I got 2.32. People, did you get the same answers? Shame on you. Oh, 2.31. Yeah, 2.319, something like that. That'll be good. Is that good? Yeah. I definitely I'm not gonna give you 3 by 3. You can see that I give you 2 by 2. How many calculations that you have to do? You have to do like 1, 2, 3, 4, like 4 separate boxes with different denominators. Okay. In this case, you never get the same denominator compared to the dice problem. The dice problem was easy to compute, expected because they're going to be the same. But that one was like, oh come on, it's just, you know, you have to compute each of them separately. They might have the same. I will give you one question for that. It's going to be the question that we're going to do for practice before I let you go. Okay, it might be the questions. I will do this questions. Yeah, this one was easy because they're giving us the same thing. Let me just double check. Yeah, I will do this one. No, it's 3 by 2, always 3 by 2 or 2 by 2. If I give you 3 by 3, that's gonna be crazy. I have to do 9 of them. I'm gonna give up for that reason. Okay, so let me just finish this part really quick for that. So we have to look for the chi-square of degree of freedom equal to 1, correct? So we have to go for chi-square 1s on the chart. And then what is the alpha? Where's the alpha? I forgot to post this. The questions right here. The alpha that we took should be 5%. Okay, and I didn't mean to eat that up, you know, but it's just I don't have enough space to write up a total for that, so I'm definitely gonna skip them a little while. So the alpha equal to 5%. Okay, yes. No, the total is like no, we don't count a total. Remember that we only count the total is it's just a number we computed to get the record. Okay, so let's say the number of males and the number of females and the number of people who eat more than 3s or less than 3 and stuff like that. So the total number does not really affect the independence test. Okay, it's only the join. Let's say the male and the number of people who eat 3 meals a day, and the female, you know, the number of people who eat less than 3 meals a day, so and so on and so forth. Okay. So when we look at the charts, what do we get? So we're gonna look at the first degree of freedom. So apparently that we're gonna go for the first one. And what is the degree of freedom? So I need this space. Yeah, I need up to this. The answer for that will be 5%. That's 1 degree of freedom. So the answer was 3.841. Are we good? Yep. So if the statistics less than the critical value, what happens, people? So statistics less than the critical values. So we're going to say reject HJ, that's it. So we're going to reject HJ. Okay.
Because sometimes C represents the critical value and sometimes it represents the column.
Oh my goodness, that is a good point. So what do you want me to do? You want me to write them down as critical value, or CRI, something like that? Maybe easier to read. Yeah, that is a good point. Sometimes you see to represent a number of categories, and in this case, I think I just put it down like critical value, so it will be making it easier for us to understand critical values. It's basically found in the chart. Is that good?
What I said, is that right? Because
yeah. So you can pick yourself number to get the number of category, but I feel like sometimes I use some numbers. I'm not quite sure. Let me just look at the notes, and I think I know use different syntax for that though. I just don't quite remember planning out this lectures. And then I use K, yeah, the K to represent the number of categories. So I feel like K minus 1, so that'd be a little better, not to get confused. What do you think? Yeah.
I agree.
Uh-huh.
But I guess we will know because you have the notes here.
Uh-huh. Yes. I would say using K to represent the number of categories is going to be a little better instead of using C in this case. Yeah, this is a little typo. Would you forgive me for that? All right. On the last page, using the DF, yes, and yes. Does that mean if the DF will always be 1? Yes, that is true. The DF will always be 1 when we have 2 row and 2 columns, correct? So in this case, the degree of freedom is going to be row minus 1 is 2 minus 1 times 2 minus 1 is 1. If I give you 3 by 3, so that should be 4 degree of freedom. So we could 3 minus 1 times 3 minus 1 is always be 4. If I give you 3 by 2, is always, or 2 by 3, so it's always be 2 degree of freedom, and so on and so forth. Yes, question.
So now that we know that we have to reject the alternative hypothesis, so can we say that we do not have enough evidence to support that they are dependent?
Yeah, they're dependent. So we do not have enough evidence to support that they are dependent. Okay, so we can just say, we cannot claim that they are dependent. I don't think I have enough space for that though. What a shame. So can I just, yeah, put it down here. Oops. Are we good? Yeah. Is that good? Yeah. So we're rejecting the fact that they are dependent, but it doesn't mean that we're going to accept their independence. Yeah, so that's a good point. That's a good point. So I always tell people, like, is that possible? If they're not dependent, so they should be independent. The answer is no. Statistics, like, it's worked differently. So the two things are not dependent doesn't necessarily mean that they are independent. So I have some counter example in terms of the dice and the coin problem, but I don't have enough time to do it to give you that definition. But there are certain cases they're not dependent, but they're not independent either. So there are a certain case like that. Okay, so it doesn't mean that they are independent. So you have to look at statistically, like especially in different angles. So there's a lot of counter example to prove that they are not independent, even if they're not dependent either. So it's actually really counterintuitive, like in terms of English. So if two things are not dependent, so they should be independent. But the fact is that the fact is that we can't accept. So this is why I never write over accept though. I can, but there's still some professors saying that we can't accept and no. The answer is no. We can't accept the fact that there's no way to prove it. So it's only for 139 people, right? Not to include that this is the study on the entire population. Remember, the study that we have to make, the decision that we make is on the whole population. And then the sum that we took is 139, right? So the only thing that we trying to do is trying to reject as many wrong things as possible. It's kind of fun. Yes, so we can prove things, but we definitely can prove that's some interesting part of statistic compared to math, basically. So now we're gonna move up to the last question. I believe I think I have enough time. Would you guys willing to stay a little bit longer? Let's say 3:15. I will let you out. Is that good? And then yeah, 3:15. The class added 4. And then let you out 45 minutes early. Really? It's okay. I wish you guys would have a wonderful Thanksgiving. And any plans, any funds with that? Oh my goodness. I got an email from my student. It was a very sad story. I wish I could tell you guys. And but she's not in this class. She's like in Mat 140. It's a approved course. And then she told me that she was in the psychic ward, so she'd have to live there for a while. She's planning on suicide. And yes, and then she'd write me letters and something like that, and then have to Google what it means by OTD, whatever it is. Yeah, I did OCD actually. And I was like, yeah, I was doing some research for that, and then I told her, like, calm down, and if you sort of feel like you're planning on do that, make sure that you pass my course first. You don't want to ruin my record. that's pretty okay. Yeah, it was something I didn't even make sense out of it. You're gonna make me sad because I'm trying to get some perfect record for my course. It's kind of scary, but I think it's getting better right now. You're gonna there's nothing really in points except for paycheck. It was pretty okay, but generally I just don't want people like to pass sales and all of this. The semester is almost over, right? And then just I know there's a lot of burdens, a lot of things going on, but just keep on doing it. Okay, so now we have a Thanksgiving, and hope that all of you going to have a great turkey and with some some let me just go to another question. I feel like this question would be a little more interesting. The profile questions. I feel like this one's going to be a lot better. Yeah. Okay. Yeah. Attitude overall great. Hopefully that, before you plan on doing something, you're not gonna ruin my record. I really need people to do well in my class. If one of them drop or not doing well, you're gonna hurt my record. I'm gonna be I don't care. I just want you guys to do well in this class though. And then the selfie problem, right? And how many selfies that you post on Facebook, on Twitter, on Instagram, and so on and so forth, right? How many angles do you take? like front, profile, 3/4. You're master at it. You might be like, I have like 1,000 angles. But when I took picture of my friend, I always pick the best position that I have with the best smiley, best faces posted, right? I don't care about the rest of them. That was fun. Early Christmas present. Yeah, I mean, I wished I have that. So yeah, so this is going to be a total for 40, right? Was it 40? And this is 40. And this is also 40. Now, the reason why I love this question, because I did it from my last class and everything was just look really, really straightforward um, from the expected number you will see. So a total number of the people who take pictures in the friends with 40 and the profile was so 40, 3/4, so 40. And then the correct position should be 23 plus 26 plus 29. What is the answer for that? Somebody help? Oh, come on. 48 plus, I'm sorry, 49 plus 29 was 78. Are we good? Is that good? And then the total number of incorrect positions. So we should have 42. The total will be unchanged. So that was 120. Okay. Okay. So this is the end, right? So this is the number of people who are under investigation. How many photos you took each day, and how many photos you post on Instagrams each day, something like that. So now we're gonna look at the expected numbers, correct? Yes, question.
What is the what do you call, what's the question? Because then we have to write the alternative and no hypothesis, right?
Yeah. The first part that we're gonna go for HO will be they are independent. Yeah.
But like, what's the question in the problem? They don't give us a question to answer. You know what I mean?
Yeah. Hold on a second. Okay. And then the second one, they are dependent. So usually they always be like that. So okay. So the questions that it asks, because I didn't copy it, so it should be testing on proportions, but it's proportion in terms of the. So let me just paste that. Oops. Let me just retake the pictures for that. Paste this here. Yeah. The question was here, like their proportions correct identification differs from 3 nodes fused at alpha 0.05. Okay, so this is what the question asking us. Is that great? Is that great? Yeah, but you don't necessarily have to work with that because this is a cost tab. You can't compare one of them to the other 3, so 4. So we have to test if they're independent or dependent. Dependent meaning that they do not have the same ratio, so that the ratio should be different. The independent meaning that they must have the same ratio. So this is pretty much the same thing. So now we're going to look for the expected, and then this is front, and this is profile, and this is 3/4. Can I do something like that? So just want to make it shorter. Is that good? Yeah, I forgot to copy the questions because I need to do something else. So I have to have enough space to write the total for each. So the total would be unchanged. So that'll be 78, 42, and 120. Is that good? So that'll be the total number of ends. And this one should be 40, 40, and 40. Okay. Is that good, people? Oh my goodness, I have so much trouble drawing this. Does it look good? Oh my goodness. Yep. No, you should say beautiful, because if you're not saying that, I'm not really in a good mood when I grade your exam. I'm spend so much time enjoying it. Yeah. Next time when I ask you this question, you say something beautiful. Yes, that's pretty much it. I was kidding. Oh, come on, we have to have some jokes. Beautiful, right? And then this is incorrect. And then, so no, now I'm going to compute the expected numbers on the first row. Outstanding. All right, so I need to go for the, that's make me really happy right now. So I need to compute this one first. I need to compute it first too, right? Because I can get the rest of them using subtract and so on and so forth. So how can I go for the first box, people?
It will be 40 times 78 divided by 120.
That's correct. So very straightforward. Now you can hear some go going. This is my neighbor. Oh my goodness! Every single time before the end, they're trying to give me some surprise, like a Christmas present or gift for that. And then we're gonna take 40 times 78 over 120. And the answers for that was 26. Oh, that's beautiful, right? And the value looks good. And then the second one was E2. It should be like E1, 2, but I just need to compute 2 columns, so exactly to put that E1, E2. So we take 40 times. Oh, it's gonna be the same. Oh, come on, I'm not gonna do it that way. So yeah, it's just 26, 26, 26. That's beautiful. We see that these questions should be given on the exam, correct? And then if they're the same thing, the bottom should be 26 subtracting 40. I get 14, 14, 14. That's beautiful. Yeah, this question should be good right now. And then we're gonna do the chi-square. So what is the degree of freedom for that though? The degree of freedom was r minus 1, the number of rows, minus 1 times the number of columns, minus 1. So we have 2 rows, right? 2 rows and 3 columns. So we have to take 2 times 1s times 3 times minus 1s. And so we're going to get the answer will be 2. Are we good? So 1 times 2 is 1, obviously. 3 by 2 is 2 degree of freedom on the exam. Yes. So now we're going to go for, so the degree of freedom is 2. So I need some help to do this part. So 23 minus 26 square over 26, correct? Over 26. And then the second one, we're gonna do the same things, correct? We're gonna do 26 minus 26 square over 26. Is that good? Oh, that's really awesome. Like all of them was 26. For the first 3 it was 26. The last 3 were 14. That was so easy to compute it. And now we're gonna do, can I do the last ones? I take 11 minus 14. I just put dots here. Is that good? And then square over 14. Okay, and I do all of these math together. We're going to get the answer, so we take 23 minus 26 square. I think I did it before. I got the answers 1.97. Is that good? All right. Isn't the row is No, we have 3 columns. So we have 1 columns, 2 columns, and 3 columns. Yeah, and we have 2 rows. Oh, it doesn't matter. It'll still be 2 degree of freedom. Come on, you're not going to give me headache for that, right? Would you? I'm just kidding. I'm just kidding. So we have 3 columns, 2 rows. So that should it still be 2. So we have 3 rows, 2 columns, gonna be the same. And then, so we're gonna look at the critical value for this, right? And then the critical values that we have should be on 2nd degree of freedom. And then the alpha was 5%. Now I remember I posted questions right here. So the alpha is 5%. So this is what we got. And then we're gonna look at them on the charts. So the chart's going to provide us with 2nd degree of freedoms. And then we should be able to get finances here. What are the finances, people? And then the 5%. So that was 5.991. Okay. Are we good? Okay. So after that, we're going to say what? Yes, so we're going to reject it, okay? Are we good with that? Any concern? So if we reject HA, so we're trying to make the ratios different, but we cannot claim that the ratio, I mean the proportions of the correct identification difference, right? So we cannot claim this fact. So we factor reject. Are we good? Any concern for that? Are we good? No concern. If I give you this 2 question like that on the exams, would you possibly get full credit for it? If I give you 3 by 3, the answer is probably no, because there's so many of them. 3 by 2 was like 1, 2, 3, 4, 5, 6 calculations. That's a lot. But like 3 by 3 was not possible for sure. It should be 2 by 2 or 3 by 2, okay, on the exam. Oh, maybe 2 by 2. Oh, come on, just do 2 more box. Doesn't hurt you that much. Okay, but it'll still be something, right? Something that we don't want to see 3 by 2 on the exam, but we have 2 questions of them. I went over a question like that as well, right? You can try the last one, the overweight and desirable weight, and then also the composite bias is something that we have, and this might be on the exams. So anyhow, when errors is over, I know it's hard, so we have to double check the calculation. I suggest that we going to make a chart like this. We take the observed minus the expected square over the expected. So we can do that, and then if you make some mistakes on it, I will take away less point, then you don't do it that way. So anyhow, so this is the entire chapter 12, and I believe that is good first before the second exam, and that's also the hardest chapters the hardest part compared to chapter 9. I'm sorry, 10, 11, and 12. Going to be the main focus for a second exam and a final exam. So that's pretty much that we have for today. So today we're going to have a classwork. The classwork should be due on Sunday, so it gives you time until 11:59 p.m. to finish it. Okay, so if you can't do it today, so that'd be great. So we can't do it today, so you take time to finish it by Sunday. Okay, so now this time I don't forget um to post it. So I do apologize for the last class that I thought I posted, I'd make it unavailable. So now we're gonna have classwork 8, and hopefully that you can finish it before Thanksgiving. So I hope that all of you is going to have a wonderful weekend and wonderful days, and you're gonna have some good party with your friends and some neighborhood, some families and all of that. Okay, and don't forget Black Friday as well. So I hope that you guys enjoy it, and take care. We're gonna see each other again on the following Saturday on December 4th. Have a great day. Bye bye.